I will try, I am not sure I will succeed, but I will try to explain physical principles of all electrical and electromagnetic methods, not only mining, but in oil exploration, in logging. It's not simple that I will be successful. I'm not sure that I will be successful. It's not very simple, but I will do my best. My long experience, almost 100 years, 40 at least, shows if you would like to understand your profession, you must understand physical principles. You must understand. Then you must understand why we sometimes deal with complicated equations. What is the reason for it? Then, after it, it's possible to understand principle of the method. What does it mean to understand principle of the method? It means you know where there can be used and where there not can be used. Why we are working sometimes with direct current method, sometimes with frequency method, sometimes with time domain method. So I will try to explain how I understand, it's my approach, my point of view. So good or bad, so you will be forced to share with me what I understand. So iron rule. I will start from, each time I start from physical laws. Second, I will come from these laws to some equations which I will not derive, but I explain why they are used. Then I start to speak about methods. I begin from the simplest case, constant electrical field, then constant magnetic field, also methods which are based, then electromagnetic and frequency and time domain. So please try to follow me, regardless what would be result. Now, first of all, I will explain the physical foundation of all electrical methods based on the use of constant current. So no time domain, not frequency, nothing, constant current. Current and electrical field which don't change with time. There are three fundamental physical laws which define in all cases behavior of the field. The first physical law, Coulomb's law. Let us check how we understand it, because I'm completely confident that all of you heard about Coulomb's law. Let us look how we do understand it. In this way we will follow next. So, Coulomb, French scientist, discovered the following law. He found if we have two charges, small charges, with respect to distance, small volumes where this charge is located with respect to distance, each charge creates force, produces force on another charge. Let us write down this law. So if I have one charge, E at point Q, that's point Q, small volume, then another charge at point P, then each of them produces force. Charge starts to move. And he found out, as all of you know, force with which charge around point P acts on charge around point Q on the point P is equal. Unit divide 4 pi epsilon naught dE Q dE P divide LQP cube LQP. So, as I promised, I will not derive any equations, I only write down. So, what is written here? Force which this charge feels. Now, what is it? 4 pi constant, epsilon naught. What is the epsilon naught? Constant. Sometimes it's called the electrical constant of free space, but it's nonsense. Free space is empty, it does not have anything, no physical properties, simply constant. In practical system of units, it's farad per meter. What is the unit of the force? Newtons. What is it? Coulombs, distance in meters. So, if this positive charge, this charge starts to move. It's a pure mechanical force, newtons. It's measured in newtons. If it's negative charge, it starts to move opposite direction. Now, that's what we learn in our school and university. Now, let us mentally assume these two charges. First of all, let us remember this law is written for elementary charges. Size of these charges small with respect to distance. Only in this case, fill the case as square of distance. And also directed along line. Only in this case. Case not very typical, but that's the case. Now, let us ask ourselves now the most difficult part, which usually is not discussed. Since you are very young, most of you, 99.999%, I am sure you remember, if you have open textbooks in physics, that's called electrostatic. So always when you write this law, you remember, you have good memory, you remember it's always in two charges in free space, no medium, so it's electrostatic. Electrostatic does not have practical relation to geophysics. So maybe this law is only useful in electrostatic. It does not have relation to our real environment. Let us discuss it. So first of all, if I ask you questions, but now time to prove that you would like to have raise in your salary or to get good grades in a university. Now I take these two charges in free space. They are small. Now we can calculate force in newtons. For example, 1 Newton. Now I'm going to ask you a question. If I take these two charges and put in conducting medium, for instance, in seawater, so no more free space, no more air, conducting medium, salt water, 0.1 ohmmeters, 0.5 ohmmeters. What happens with force with which this charge, watch how I'm speaking, saying, this charge, I'm asking, what happens with force with which this charge acts on this charge if instead of free space, there is seawater? The same. Why do you think it will be the same? Why? Everybody agree? The same? I will not care whether you answer right or wrong, but I need explanation. Why?
The charges are the same. The charges are still the same charge.
The same charge. Aha.
But the Coulomb figure will be different because
Sorry?
the Coulomb figure you're using is Coulomb
So, but the absolute not will be different.
because you're in a different medium. Another free space.
That's better. Even answer is wrong, but that's better because that's what I would like to hear. So let us say there are two different points of view. But let us learn, for some of you know perfectly, I expect, let us learn how to read equation. Epsilon naught, what is it? Parameter of the medium or constant? Constant. So it means this equation does not contain any parameters which depend on medium. Therefore, we cannot say what you would like to say. This Coulomb told us, and as I like to say, we have to respect great masters. That's iron rule of learning. Never argue with masters, great masters. That's very simple. As soon we are wrong only when we start to argue with them. When we bring our own personal interpretation, then we are in trouble. That's the main, only one distinguished quality of great masters. Never argue with them. So, it's constant, the same constant as 4 and pi. So, this force with which this charge acts on another charge is the same everywhere. Put charge in clay, another charge in sand. There are many interfaces. This law, this force caused by each charge remains the same. That's first fact which follows from this law. Now, all of you right and wrong. In effect, force with which this charge will feel will be different. But why it happens? Because some new charges arises. We will not speak about them today. Now, not today, now. It's important. This force which exerted by given charge on another charge is independent on the medium. So our brave extrapolation, this law can be used in our environment, in our conducting environment. That's point number one. Point number two. It's a constant field which does not change with time. Can we use this physical law in electromagnetic fields or not? For example, I have frequency 1,000 Hertz, 10,000 Hertz, 100,000 Hertz. Can I use this physical law? What do you think? Even we cannot use it.
So we use it at any instrument of
Always? Always? No. No. But, and we will do, as soon as we assume always, it means we assume that only charge creates electrical force. But that's not the case. We will come to it. But fortunately for geophysics, for our profession, in most cases, with extremely small error, which we are not able to detect, we can use it. But in such method as radar, as the electrical logging, and others, we cannot use. But in most methods, we can use. We will come to it. So, that's two generalizations which are very, very for us important. Now, that's beginning of all theory of electrical methods. Now, let us make next step. Mathematician came to conclusion. Physicist, not mathematician. This charge, for some strange reasons, acts on this charge. How it happens? And what is going on? He then came conclusion whether we have here charge or not, this clever charge creates something around. And this something is called electrical field. So next step, that's step number one. Next step is, let us consider force divide force at some point, divide elementary small charge, elementary ratio. And this ratio has name electrical field and nothing else. So behind of this simple arithmetic, fundamental physical fact. If you have here charge, it creates at each point force. When we will put another charge, it starts to move. So second charge is only indicator of presence of the force. So let us write. Second step, that's electrical field caused charge divide LQP. Cube LQP. That's electrical field caused by elementary charge. That's what is the subject of our measurements. That's about what I'm going to talk through course constant field or electromagnetic. First of all, unlike Newton, force which is measured in newtons, electrical field is not exactly force per unit of charge. And this quantity has dimension in practical system of units. Since we are working in applied area, it's reasonable to use practical system of units, volt per meter. Now, so that's the beginning. If according to this, it's not more Coulomb's law. Coulomb's law was here. That's already generalization, small generalization. Now, that simple expression due to elementary charge. So due to elementary charge, fill the case as unit divide square of distance. Does it take place always? No. Only in this special case. In all other practical cases, it does not take place. So suppose I have some volume with many charges. How to write expression for electrical field? Electrical field is equal unit divide for epsilon naught volume integral LQP cube LQP. So I perform summation. If you look in this expression, it does not tell you the field decays extremely quickly as unit divide L square. It could be constant, it could be zero, it could increase in some direction, decrease. So that's what is important to understand in geophysical practice, in electrical methods, how field behaves. Now, again, this expression is valid always for constant field, conducting medium, non-conducting medium, dielectricals, everywhere. It's valid inside, outside. It turns out that in our practice of electroprospecting, we mainly deal with so-called surface charges. We don't have practically volume charges, only surface. So in the case of surface charges, expression has the following form. Surface density of charges, right? LQP cube ds. So far clear? Clear? Completely clear, or already infinite distance between lecturer and students? Clear? I'm speaking about classical facts from elementary books in physics. So if you don't feel comfortable, ask me. So what is it? It's a density, charge per unit area. That's distance between, for instance, that's charge. That's point Q, that's point P, and QP. So I simply use principal superposition and calculate field due to each element. Now, that's this expression we are going sometimes you will not use. Now I would like to make 2 points. I almost did everything from Coulomb's law, but I missed 2 important points. Point number 1. According any of this simple equation, what creates constant electrical field? If I ask you this equation, what creates the electrical field? Well, very simple equation. Charges. And we have bravely say charges, you don't have electrical charges, you don't have electrical field. Charges, father and mother of electrical fields. Simultaneously, father and mother. Not two types. One generator of electrical field. So when we are going to the field, in borehole geophysics, surface geophysics, whether we perform Misalamas or symmetrical Schlumberger profiling or different types of logging, if we measure electrical field, we must say somewhere there are sources of this electrical field. Otherwise, we would not be able to measure. Fortunately for geophysics, all these sources are located in the right place. I'm talking about electrical methods based on use of constant field. And where these charges are located? Sorry? Even the electrode, it's not too bad, it's good, but it's not useful. Who cares where electrode is located? Yeah, unfortunately, we have more brave goal in electrical methods, not to find place where we put electrode, but we have to find more serious places, such as surface of semiconductor. So could you say, it's correct, but could you say, when you say on the surface of conductor, it means what would be another medium? Huh? Conductor is not ground? Huh? So let me help you. I'm sure all of you are right, but fundamental point is all these charges arise at interfaces, not boundary between conductor and insulator. Everywhere where there is a contact between formations with different resistivities. So you see how it becomes interesting. We measure somewhere field caused by our sources at interfaces. What is the main goal of geophysics, electrical methods? To find these interfaces, to find what is the shape of them, what is the depth, where they are located from point of measurements. So, one is important facts of Coulomb's law is electrical field is caused by real charges. It's not to visualize this fact. That's fundamental difference between mathematical and physical approach. You measure quantity, electrical field, more precisely voltage, and it's caused by sources, real physical charges. That's not invention of mathematicians or who knows whom. It's a real physical fact. For instance, in gravity, this device creates gravitational field. Try to pretend that there is no masses here. No way. You have to accept there are masses with some density. And due to these masses with density, for example, 2,000 kilogram per meter cube, these masses do create gravitational field. Exactly in the same manner, real physical charges, it's not important we don't see them, but they exist. We can measure them, which arise at interfaces, create electrical field. That's one point which it's not too bad to remember, because I will go in electromagnetics with this approach. All geophysics, all interpretation, solution of inverse problem, processing data is the one goal. You know field, find generators which created this field. Nothing else in all interpretation. All methods, clever, simple, good, bad, are based on the same approach. in seismic, in gravity, magnetic, electrical, you have field. Please find where are these fathers and mothers of these fields. Now, there is another point. I told 2 points of view. Another point is we have to be modest. We know equation. We know that this charge creates electrical field, but who knows how this clever charge through this space, air or free space or who knows, create force. My point of view, nobody knows. But that's the fact. We are engineers, have to know only physical law, how to calculate this field, where it can be used, where it cannot be used. So 2 points of view. Last point is clear what I told, or it's a mess? If I ask you, that's mass, does it create gravitational field at this point? Can you explain me how this clever mass creates here gravitational? So here is the place where we don't need to argue with nature and leave the subject to great masters to discover it. But we are engineers, have to know how it works. That's great sin, don't understand it. It means we are becoming not engineers but plumbers. So exactly the same story with Coulomb's law, Newton's law, Coulomb's law. We know equations, we understand where apply, where not apply, but we don't know how it works. Now, let us speak about behavior of electrical. You are not tired? Maybe questions? I will rest, you will ask. Remember about what you were told. If you don't ask questions. First of all, how is my beautiful Russian accent? Your Australian accent also works very well. I don't understand anything, so ask me questions slowly. So we have mutual equilibrium, democracy. So please, do you follow me? So my first goal was to describe there are 3 physical laws which govern all electrical methods. Coulomb's law, principle of charge conservation, and Ohm's law. Only 3. So with one law I almost finished, but not completely. So if you don't have questions, let me continue. But you will be guilty if you don't understand. So let me take this expression or this expression. It's electrical field caused by charges. How electrical field behaves, that's important for us. Suppose instead of gravitational mass, do you agree with me here there is gravitational mass? So there is electrical charges. I start to move my point of observation. What happens with electrical field? It starts to change. If I ask you mathematical question, electrical field, then I'm not asking how field changes. Who knows? Maybe near with these charges it does not practically change. Then far away it starts to change very quickly. That's what I don't ask. I ask one question. What happens? Not what happens. Is it continuous change of electrical field or discontinuous? Continuous. Continuous, it means you change a little and field changes a little. You practically don't change, field practically don't change. That's simple secret of continuity. Now question arises, are there places in electrical methods where all time, even I speak about Coulomb's law in general, I think about geophysics, nothing else. So are there places where electrical field behaves as discontinuous function? It turns out there is such place. And let me, again, I will not prove, I only tell you. So there is one case. And it's not difficult to understand. For all cases, for instance, these cases are interfaces. between layers with different resistivity. And theory tells, very simple theory of electrical field tells, if you watch behavior of normal component electrical field, which is perpendicular to the boundary, normal component electrical field is discontinuous function. What does it mean, discontinuous? From both sides, field is different. And this is one fact which I would like to emphasize. And then another example. Much more important. This example is, we have interface, piece of interface, plane, not plane, anticline, fault, plane, doesn't matter. If we have here at some point electrical charge with density sigma, that's density, sigma. Density charge per unit area, Coulomb divided by square meter. If we measure electrical field above and electrical field beneath, that's normal. It turns out from both sides, normal component electrical field is not the same. And theory tells difference of normal components from both sides is equal density of charge divided by some constant, epsilon naught. So what is the important? Always, without any exception, C bottom of C and bottom. If you measure electrical field in water new interface from both sides, normal components are different. And what is amazing, this difference is exactly equal density of charges. So let us remember this fact. Now let me summarize. First of all, what we did. I described you Coulomb's law. I told you it declares a constant electrical field is caused by charges. I hope after meeting with me, you will not tell electrical field is caused by current. For instance, there is one of the lovely scenarios, electrical field is caused by current. No way. If you think in this way, it means you invented new Coulomb's law, but name must be changed. Instead of Coulomb's, yours name. So that's only one scenario, very pleasant. So that's first fact. Second, Coulomb's law is valid always for constant fields. Conducting medium, uniform, non-uniform, always. Third moment, without proof, but we will come later, this law is working for good or for bad for almost all electromagnetic methods. If there are alternating charges, they do create electrical field. It turns out these charges create electrical field according to this lovely Coulomb's law. Now let me consider with you one example. But before I consider this example, Peter, would you be so kind to tell me when we will make break each 40-50 minutes?
We can do that. Short break each 50 minutes.
50 minutes. Yes. Do you agree? So we have a couple minutes more. Let me ask you one example which you are going to consider is a great practical and theoretical importance. If I ask you a question, how we solve forward problem in gravity? Who knows? What I told, it's clear? Question is not clear, so please at least tell quickly that you don't understand what I'm telling. It's no harm to me. So, my question is, I would like to solve the forward problem in gravity. What physical law is used to solve the forward problem in gravity? So not Newton's, but what follows from Newton's law. Everybody understands? So let me write down what you told, if we will check how we understand each other. Just a second. I know everything is okay. Suppose I would like to find gravitational field due to this object. So you suggest, who can dictate me how to find gravitational field due to this object? So I write gravitational field at some point P. P is a point of observation, profile. Tell me please how to, that after we will answer this question, we will make break. How to solve the formula problem. First of all, students, because they are youngest, they have excellent memory, and so how? And then we will ask old engineers who are very old here.
Require a reference mass.
Sorry? No, that's my mass. Or this chair, or this table, or my body, or this. So how to calculate this constant? Okay, I will follow. I make some adjustment. I will write minus with your permission. Agree? 4 pi. Gamma, for example, who knows? Constant. Then what next? But I'm here, and that's mass of the object. From this mass?
Yeah, from
this mass.
From your reference.
So, not the reference, just a moment. That's mass. I'm a little worried about what reference. So, maybe I don't know this one. So, that's point of observation. This is the point. So, I honestly wrote constant. Now, even let us write without 4 pi minus gamma, practical system of units. Now, that's my mass. That's point of observation. You see, all of you see pointer, ink shows. Now, I am ready. Dictate. How to calculate this damn gravitational field which all of us attract to each other? So,
divide by distance
between this point and
the center of
okay, I'm ready. Center of the mass. That would be your physical law. Newton's never thought about it. Now, so who is? But I'm ready. So everybody agree to the center of the mass? Huh? So I hear some hope in the right direction. Huh? Oh, because Coulomb's law as well as Newton's law were developed only for elementary mass. For mass, I mentioned at the beginning, now we are checking, that volume of this mass, volume must be much smaller than distance. Why it's important? It means you don't care where this mass located inside of the volume. So before calculating gravitational field, you have to divide this volume in many small elements. And then apply for each element Newton's law and then perform summation. But regardless in which continent I teach, I don't much travel. But each time when I, in School of Mines, have class, I have already 17 years only in United States. 17 years. Each time, everybody wants to change Newton's law and suggest center of the mass. Well, so, if I write with your permission, that would be correct. Density, volume, dV, elementary mass, and cube distance. Now, tell me please, Did we solve forward problem in gravity using this equation or not? So, first of all, what does it mean to solve the forward problem? Maybe we are in trouble with terminology. So we will resolve it with my good friend trying to help me also in this way. So what does it mean? I ask him mainly students, and then higher level.
Given a situation, you solve for the field or whatever.
Correct. So the solution of the forward problem is determination of the field when you know generators. In case of gravity, masses. That's the solution of the forward problem. Without solution of the forward problem, no way practically to solve the most important for us problem, vice versa. Knowing field to find generator. Generator means all body interfaces, etc., etc. So, it turns out in gravity, Newton's law is beginning and practically end of solution of forward problem. You can define, if you know masses, if you assume you know masses, use this simple equation, and that's it. In all theory of solution of forward problem in gravity is done. Go to computer, calculate this integral. If you can simplify it, that's it. No equations, very simple. Natural question arises. The same situation with Coulomb's electrical field in Coulomb's law, because Coulomb's law looks like as Newton's law. Integrate, that's it. But fundamental difference. And this difference we will discuss after break. Let us stop here. One physical law, which is foundation of all electrical methods, surface and logging in oil industry, everywhere. Now, then, before going to another laws, my goal and your goal, mainly your goal, I will only help, to understand why we, on one hand, must understand Coulomb's law, but it's useless in order to solve the forward problem. Again, let us make clear for everybody. What does it mean, solution of forward problem? It's determination of electrical field, or magnetic, electromagnetic, seismic, doesn't matter, when we know generators, when we know model. Why it's vital? Very simple. Otherwise you will not solve inverse problem. In other words, you will not perform interpretation. Please imagine situation, not ancient time, not medieval time, but now. How engineers is making buildings or bridges. Suppose for a moment that engineers who is involved in building bridges don't know how to choose material, how to make bend of the material. He does not know what would be the traffic. He does not know what the weight of train, etc., etc. In old time it was very simple. Only people mainly walking horses. So all in other areas, as for example, strength of materials, each professional must know how to find parameters of the bridge. He must know parameters of the road. He must know parameters of the buildings in areas of high seismicity or small, doesn't matter. So in other words, in all professions, without engineering professions, we do solve the forward problem. We do. Sometimes we call it forward, sometimes we simply calculate parameters of the bridge, but the solution of the forward problem. Now, the same we have to do, and there is no way around. Now, back to gravity. in order to find field, gravitational field, fortunately for those who are involved in gravity, they don't need to know, from a mathematical point, anything except Newton's law. There is no any equations, nothing. You have some mass, volume, salt dome, for instance, with some, you say, density of salt dome 2,200 kilogram per meter cube, a reasonable number. So I would like to calculate gravitational field, and I directly use Newton's law. Gravitational field equal gamma volume integral delta V LQP cube LQP. That's point Q, that's point P, and you use this integral or some more simple expression, but in effect this equation, and you will calculate at each point. Inside salt dome, outside salt dome, you can do it. Coulomb's law looks like Newton's law, but it's useless. That's what we have to understand. Otherwise, a lot will be not clear. I will try to do it without any derivations. In order to explain you where is the end in gravity, only beginning in electrical, I have to describe you the first very important phenomenon which takes place in electrical fields. So, do you understand the goal, the purpose? Everybody understands? I have to explain why we have to use heavy guns. That's the goal. Heavy guns, yes. Clear? Good. Ask me. Don't worry. Ask. Now, please imagine, unfortunately we don't have it, glass of wine. You see, all of you see, some eyes I see even spark. So, I didn't tell what type of the wine. Sort of the wine. So, glass of wine. Glass, from glass, wine, or beer, or your beer. And let us do the following. Please remember, I didn't take piece of metal. I can take piece of metal, but what I'm going to show you is valid always, as soon as we are dealing with conductor. So, that's our conductor. I would like to forget about glass of wine, otherwise you start to think in the wrong direction. And let us take charge. Electrical charge, 1 Coulomb. 1 Coulomb. Let us be careful. I will take, each factor is important. First factor, it's a non-conducting medium. For example, air. Air is not conducting for our purposes. That's conductor. Doesn't matter what conductivity. It could be piece of clay, piece of sand, even granite, because it's also poor conductor, but conductor. It could be again glass of wine, for those who would like to again to go back to this direction. So water, not distillated water, but water which we drink. And let us ask ourselves, what would happen in this case? What would happen? I am going to consider phenomenon which is called, how? Who knows? The electrostatic induction. I need it for two purposes. Main direction I mentioned, and also practical importance. So free space, non-conducting medium, conductor, not necessarily metal. It's salt water, simply water, piece of rock, doesn't matter. What would happen in this case? Conductor, suppose iron, anion, positive. That's charge. Does this charge create electrical field? Now, do you remember first expression for electrical field due to charge? We don't care there is interface, medium, because Coulomb's law does not contain parameters of the medium. True? So there is electrical force. If it's positive charge, what happens with this lovely ion? It starts moving, right. That's iron rule, positive charge moves in direction of electrical field. So we start to see movement positive charges in this direction. There are negative ions. They start to move in opposite direction. Now, so we will have here accumulation negative charges, here positive charges. Correct? Now, we have our primary electrical field. Let us call primary due to this charge. But since charges appear at the surface, they also create electrical field. They create outside and inside. True? True. What is their role? They create secondary electrical field. And it's directed, according to Coulomb's law, in opposite direction. Therefore, what happens with total electrical field inside of the conductor? It will tend to zero. Ions are not very clever. They move under action of total field. So if total field decreases, therefore electrical field does decrease. True? So this process of accumulation of charges at interface will continue until electrical field inside will become equal zero. This phenomenon is called electrostatic induction. Now, very soon you will see how it's important from theoretical and practical point in electrical method. So it will be historical moment when field inside, not outside, inside, will be zero. Now, so how it happens? It happens because this clever, now I'm talking about cleverness of these charges. These clever charges are distributed in such peculiar way that at each point electrical field due to them and primary electrical field is equal zero. That's all what we know. If you take piece of metal, it happens very quickly. If you take glass of wine, it will happen, but a little slow. If you take quartz, it takes too long, but it happens finally. So in any conductor, it happens. In effect, I speak about transient method, but not in this content of this lecture. So, one thing we do know. Finally, electrical field inside will be equal zero. And it happens due to surface charges. This charge itself do create electrical field, if you still believe in Coulomb's law, because again it does not contain conductivity, it does not contain electrical constant, but in order to make it zero, surface charges are distributed in such way that total field at each point compensate primary. This amazing phenomenon, of course, used in techniques, etc., and it's called electrostatic induction. Let us look at this phenomenon from 2 points of view. You take charge. You know this charge. You know, because you are physicist, geophysicist is a greatly physicist, you know at interface charges, surface charges arise. Now, let us forget that this medium is not conductive. Suppose we are smart enough to measure in non-conducting medium electrical field. Point P. At each point, electrical field will consist of two parts. Agree? Two parts. What is the part number one? Girls? What is the part number one? Primary, which we know. Good. Which we know. We always know primary field. In electromagnetics, magnetic, do we have secondary field which does contain information about conductor? Field caused by these charges, correct? So let us, according on Coulomb's law, write it's equal 4 pi epsilon naught surface integral sigma q LQP ds. I use only Coulomb's law. That's point Q, another point Q, that's point P. So use Coulomb's law for elementary charge, perform summation, and if you can use this equation, you solve the forward problem. Then you can measure electrical field using clever voltmeter, which can measure in free space. Compare experimental data with this data. You solve next what? Inverse problem. Everybody follows me? Clear? Otherwise you cannot find what is the shape conductor, what is the case. Now I would like to ask you a question. What do you know about distribution of these charges? What is written here? Density of charge. It could be 1 Coulomb per meter square, half Coulomb per meter square. It could be positive, it could be negative, correct? Now, in order to find electrical field at any point or to solve the forward problem, I must know what? I help you. Charge distribution simply at each point. But what do we know about these charges? We know something. If you remember, an hour ago I told you about relation between surface charges and normal component electrical field here. Let me take this point, Q. What is normal component electrical field inside conductor? Huh? Bravely, 0. Why? Because field is equal to 0. Electrostatic induction. Therefore, normal, tangential, everything is equal to 0 inside. So, we have normal component electrical field outside of conductor. So, if it's my conductor, inside we know 0, outside there is normal component. We know that normal component electrical field E external outside at some point Q equal density of charge at this point divide epsilon naught. So we have two lovely equations. Let us everybody understands because I'm not playing game with formulas. You see, no formulas practically. I touch the fundamental questions which engineer must know. Not theoretician. It's not interesting for mathematicians, not for physicists. For us engineers, important to know why we are forced to deal with heavy guns. And that's the reason why I chosen this example, the simplest example. Watch. In order to solve forward problem, I have to find primary field. No problem, we always know. Then this part of the field, which contains information about conductor. However, in order to know this field, we have to know, as you told me, distribution charges at each point. But what we know from phenomena, we know a very general statement. These charges are so clever. They are distributed in such way that field inside is equal 0, but no slightest information information what is the density of these charges. Clear? So, in order to find field, you have to know these charges. But this equation tells you, in order to know charges, you have to know field, total field. So this problem I call closed circuit problem. Does it in this definition does sound clearly or not? What does it mean, closed circuit problem? You're taking for head, that's tail and the back. So you have to find electrical field, you have to know charges. But in order to find these charges, you have to know field. So that's Coulomb's law. It turns out it's useless. There is a difference between right, equation is correct, law is correct, and useless. It's correct. It correctly describes a relationship between field and sources. But you cannot use it for solution of the forward problems. That's fundamental difference between gravity, in most cases magnetics, and electric on one hand, and electrical electromagnetic methods. My suggestion is, I will stop for 1 minute, and you have to raise couple questions. I have to be sure that you do understand it. It's a fundamental moment. If you don't, we are in trouble. Because next I will consider today, layered medium, or body. I would like to solve the forward problem. I am engineer. I don't want to use programs which brought me somebody else. That's parasitical way of life of engineers. Engineer must understand. And then after it, only use programs, algorithms, etc. So, you have to understand this is example, the simplest, not very typical at all for electrical methods, but it must, my goal is to use this example in order to illustrate the problem of solving our interpretation, forward problem, using Coulomb's law. Clear? Or lost? I need one question from point of politeness from your side.
Alex, does everybody understand why the electric field is zero in the conductor? I know most do, but does everybody? Everybody doesn't?
Now, it's also, that's physical part. Now I'm interested by trying to open the door in order to understand why we have to use very complicated equations. We will not derive them. I will write down. But we have to understand the cause. Otherwise, it's a simply mixture of formulas. So you don't have such phenomenon in gravity. In gravity, we can specify. We have salt dome. Our experience tells us density of salt dome around 2,200, 2,400. There is small difference on the top and the bottom. Maybe many interesting phenomena, but we can. Each formation has certain at least range of change of density. But here, please imagine the same conductor, the same. I don't change shape. I don't change dimension. Only I change position of my source. What would happen with charges here? Will they change or not? Change distribution of charges? Yes, because primary field change, but essence of electrostatic induction is to make field inside is equal zero. Primary field changed and secondary change. Therefore, distribution of charges was changed. So for the same conductor, we can obtain completely different distribution of sources, Please imagine such situation in gravity. You have solid bond, and that's it. You have fall, that's it. If it's made from some known formation, we know density, at least range of change of density. Completely different story in electrical methods. So, yes, please.
If you are looking at, say, the universe when it began, when it was just a gas cloud, would that be analogous to the electric field now where the density distribution could change?
Sorry, I didn't.
We're talking about, when you talk about gravity, you're talking about solid objects.
Yes.
If the objects are not solid, does this...
Oh, yes, it will be similarity then if it's not solid, of course. Sorry? Yes, also, correct, yes.
Don't the churches, aren't they very polite and like to distribute themselves and even the charge distribution
Yes.
would always like to be ordered or in a
One side. Phenomenon is very important for us geophysicists in practice. So a little rest about physics now. Let us imagine everybody knows four-electrode array, Schlumberger array. Did you hear about approximately? I know Australia, everybody likes frequency, time domain, etc. But there are excellent DC methods. Very often they are extremely useful. Sometimes they are not useful, but there is no method which always is useful. Correct? So let us take four-array four-electrode array, typical Schlumberger array. We will discuss about it. So here current, here we measure voltage. I didn't define what does voltage mean. I hope you will help me later. And now we measure voltage. Voltage between point M and N, correct? VMN. Now, what does voltage mean? Who can tell me what is the voltage mean? There is voltage, there is voltmeter.
The difference in the electrical potential.
Punishment I will delay a little later. So can you help me? Can you give other definition? Let me tell you something. Let me tell you. Voltmeter is called because it measures voltage. That's genesis of what voltmeter. So it's not too bad to know what does voltage mean. Voltage has one definition. I will return to this point because everything is useful. Voltage is a very clever quantity. Integral from point M to N times electrical field times distance. Look from the top, from heavens. it's small deviation. That's not what I wanted to say. So M, N, and there is a wire which lay on the ground. That's voltmeter. At each point there is electrical field. There is a wire. Electrical field could be here. At this point could be here. So please remember, voltmeter is an outstandingly intelligent device. First of all, it's a little arrogant. It does not know what does potential mean, because it's people invented. Now, voltmeter doing the following. It takes wire from MN, mentally divides wire in many pieces mentally. Then takes dot product. You still remember what does dot product mean? Electrical field times length of the wire. It's equal E dl times cosine E dl. Angle between them. Don't think that electrical field which we have on the surface directed along wire. Now, electrical field does not know about mood of operator or technician who put wire on the ground. So, electrical field is caused by charges, interfaces. So, electrical field at some place could have this direction, wire power in this direction. So, voltmeter mentally divide wire in 10, 20 elements, then take dot product from each piece of the wire, take magnitude, distance, cosine, then perform summation along this wire. If that's clever voltmeter is doing, and nothing else. Everywhere, we will discuss about loop, time domain, frequency, exactly the same. So that's what, but I didn't want to discuss this subject. It arose by chance. I will return back about potential later. So now we measure, voltmeter measure this voltage. That's voltage, Vmn. Does it depend on electrical field? Oh yes. Now please imagine you are not here, outside in the field, beautiful weather, blue sky, and suddenly clouds appear. So let us show these clouds. These clouds, as usually in most cases, in many cases, especially before thunders, etc., contain electrical charges. Sometimes very large charges, and the height 1 kilometer, 2 kilometers, half kilometer, who knows? Now, so you measure voltage, you all your attention to the ground, but above moving clouds, which sometimes, yes, have charges. Question, this charge create electrical field inside or not? If it creates electrical, do I read correctly movement of the head? So does create electrical field. Very good. So creates electrical field. Therefore, it affects on our measurements, and therefore our lovely measurements, which must depend only on geoelectrical section beneath, become function of charges on the clouds. Especially, you have to watch change of the voltage. Clouds are moving, they're approaching, distance becomes smaller. Then again leave. So voltmeter must show you different signals at different times. And that's the end of electroprospecting. But there is a lovely electrostatic phenomenon, electrostatic induction phenomenon. What does it tell? Air, non-conducting medium, non-conducting medium. Earth is conductor, conductor. Let us apply what I told you 10 minutes ago. What must happen at interface? When we have here charge, what must happen? Sorry? Correct. Charges must arise. We don't know density of these charges, but they always do exist here. If they are distributed, again, in such clever way that electrical field caused by these charges plus induced charges inside will be 0. And they are saved. And voltmeter will not be sensitive to the voltage. So it's not too bad to know what saves us, even we don't know about it. So that's two sides of this phenomenon. But that's something additional from practice. So everybody understand this charge is huge, could be huge, and does create electrical field, but there is a phenomenon, number one, we will consider two more, that together with induced charges on the surface, total electrical field inside of conductor is 0, and therefore voltage is not subjected to influence of clouds. Charges, clouds. If you don't have questions, let me move, please. Very good.
That's only considering that the response is instantaneous. What if there's a time lag?
Sorry, I am slowly.
The response of these charges, distribution of charges within the ground is instantaneous. Are they instantaneously going to realign themselves so that the field will be 0?
Oh, I understand. Now, it never happens instantaneously. Never happens. But time is so short that our equipment does not know about it at all. When I will speak about propagation waves conducting medium, about quasi-stationary field, which we mainly use, I will speak about this part. So let us assume, for simplicity, instantaneously. But instantaneously means it happens during so short time that we don't measure during this time. We measure what happens after. But now, so back to main part. What to do? We have simplest electrical field, not electromagnetic, not time domain, not frequency, pure electrical field, and we are in trouble to solve the boundary problem. How to avoid this problem? Who knows? What your teachers taught you in universities, etc. How to resolve this trouble? We have to solve. Engineer must know how to solve the forward problem. How to, yes?
Take the field equation you put up before and specialize it for a solution on the surface.
So slowly, please tell me.
I'm not sure I've got the question right.
Now, question is, I have conductor, or I have conducting medium, 2-layer medium, 3-layer medium. I have conductor inside, target, mining, prospective. Simply. But we didn't approach it. We have our body, surrounding medium, overburden. How to calculate electrical field? Even not electromagnetic, constant electrical field.
The field equation you had written up before and specialising solution for that on the surface of the body.
But I don't know density of charges. I know do charges arise at each interface, 1, 2, 3. But this equation contains unknown charges.
But it's a two-stage process. I guess I'm thinking about is sort of like the surface integral equation solution.
I see. So behind of your suggestion, I think it's a very good idea. Using two equations, not one, two, which I wrote, to make something in order to get integral equations over surface, correct? Correct. but it's a special approach. It's a special approach. Let me speak about universal, which will bring us to, can bring us. So, but it's amazing difference between integral equation and Coulomb's law, correct? Now, so let us do it. So, subject is outline general approach in order to solve forward problem. What I'm going to do, it does not depend on electrical method, electromagnetic, everything is the same, in seismic and everywhere. Hydrodynamics, everywhere. Mathematician last century discovered two amazing tools. Two amazing tools. Only two, not three, not four, two. But before, let me tell you something else. We can consider gravitational field, magnetic, electrical, electromagnetic, seismic. Each field is vector field because it's described by vector. And nature tells each field in principle can cause by two types of generators. Only two, not three, not four, not five, not one. One sometimes, when we are lucky. But in general, two types of generators. It's impossible practically to imagine real physical fields, physical which exist, if it's not caused by two generators. One generator has name, and the second has name. One of them is called how? Charge is an excellent example, not necessary charge, but excellent example one time. What is the second? Vortex. Correct. Nature knows two types of generators. Let me write you. Source and vortex. Don't pay attention. Unfortunately, you have to know both of them. Now, one example of such type of sources is charges, masses. But there is another type, vortex. Beautiful example, we will speak about beautiful three example for our purposes is conduction current, current of moving charges. Who knows second type of vortex? Vitally important, otherwise you will not see each other. Simply don't see, your eyes will be, all of us will be blind. If we don't know one important type of vortex. What is it? Displacement currents. Did you hear about displacement currents? Never? Amazing. Did you take course physics? So that's the second type. There is another powerful type of source vortex without which we would not able also to see each other, and what, for sure, as geophysicist, you would be unemployed. Simply, rate of change magnetic field with bravely time. So already three, I gave you conduction current. There is also another type of vortexes, molecular currents. Without it, you would not be able to perform magnetics. So each time we have, in general, we have two types of generators. Again, father and mother of all fields. And mathematicians discovered this fact everywhere, in seismic, magnetic, radic, electrical. Since there are only two types of generators of the field, mathematicians invented two tools. one of them allows to calculate amount of one type of generators, sources. Another allows to calculate another type of generator, vortexes. You follow me? I'm doing what practically impossible, without equations to explain you essence. But it's not too bad to know. Now, let me write down these two tools. Very simple, awfully simple. Suppose I have vector field M. When I write M, I mean gravitational, electrical, magnetic, not simply abstract letter M. It's not too bad. One of you can think about gravity, another about electrical, magnetics. So don't think about only something abstract. That would help. It would not help if you don't think about abstract things. So mathematicians invented the following tool and proved. If you have arbitrary surface S, closed surface S, closed, and take integral and this, how this integral is called? Or this product, who knows it? There is a word, flux. That's good word, flux through closed surface. This flux with accuracy of constant tells you amount of sources inside of this surface. So, please, let us do together. So I will here amount of sources. Even I write letter M. Letter M. Let me do the following. This room, I mentally imagine surface, closed surface. All of you follow me? It does not need to be made from something. It's a closed surface. What is the flux of gravitational field? Through the surface. No, through this surface, yes. Excellent, zero. So this is an amazing, clever integral. It does not care. Please imagine surface. It does not care what is the gravitational field at each point of surface. Does not care. It does not care how surface is directed. This is the vector. So if it's a surface, that's ds. Let us remove ds times unit vector n up. So it does not care how field directed. Here, here, here. It does not worry about change of the field. It does not worry about direction, magnitude. It has amazing quality. If you take this integral, sum, over closed surface, it tells you only one fact. Whether you have sources of this field inside or you don't have. I call it litmus test, litmus paper in chemistry. You know from at least chemistry, litmus test you know, I hope you know. It's indicator, it's a ball, light. It shows if this device, clever, it's a S device, S voltmeter. Now if it measures this integral, it tells you, do you have something inside or you don't have something inside? Do you have sources? It does not tell you how many sources inside. No, how they are distributed, I'm sorry. How many it tells you, but it does not tell you how they are distributed. It could be located somewhere in one corner, another corner, another corner. Even it could be, if it's charges, some of them positive, some of them negative, so it gives you total amount. But what is amazing, mathematicians discover this fantastical tool. Then, let us speak about, I have to tell you about it. It's not too bad to know. I expect, taking into account your not very advanced age, you have some curiosity, and you will remember about these amazing tools in physics. It was done last century, not this century. So now when mathematicians discover this amazing tool, which if your M replace M electrical field, it tells you how many electrical charges inside. For instance, if again I take this surface, no charges inside, 0. If I have charge here, it will give you total amount. So amazing thing. Surface, arbitrary, you don't care about shape, you don't care about value of the field, but it's a beautiful indicator. So it's a bridge. For example, for electrical field, it's a bridge between sources and field. This equation is the bridge. Now, curiosity grows up. Well, it's beautiful too, but maybe there is a tool which tells you not only amount of charges, but how they are distributed. So it's possible to do it. Let us assume we take small surface, small volume, very small volume. For example, in gravity, let me take not this volume. That's too big. Let me take small volume, the surface which surrounds this volume. What this integral will show? Total amount of mass. Now let me make very clever step. Divide this integral in gravity, for instance. Surface closed, divide by volume. What we will get? What we will get? Mass we got, integral gives us, I'm sorry, there is no enough room. So gravity, the S, gives us always some coefficients, let us say mass, inside of the volume. Now I took very small volume. I will explain what does it mean I take small volume. It divided by volume. What we will get in this case? Oh, that's great difference, not mass, but density. Correct? So our next step, we take small volume, divide by volume, delta V, and we got density. Now tell me please, if I prepare you to Maxwell equation, that's what I'm doing now. Tell me please, if I have not very small surface, or this surface, but that's mass, if I divide by this volume, will I get density? Huh? So again, that's my piece of material, mass, M. I take this surface, closed surface S, calculate integral, I will get total mass, but now I will divide by this volume. Will I get density or no?
You get density.
I will get high density or smaller density? Much smaller. Volume is huge, but only the mass is located in one small piece. So I have to take sufficiently small volume. It could be radius of moon or radius of the earth. It depends on distribution of the mass, correct? So if I assume that inside of the volume mass is distributed uniformly, then take this volume, divide this integral by volume, you will get very famous quantity. An engineer must know. How it's called? Electrical, magnetic, gravitational, seismic, doesn't matter. It's universal. That's the reason why I decided to tell you. Otherwise you will not be able to understand, at least recall. It's a simple, only you have to accept. Last century, mathematician discovered this amazing fact. Take integral over closed surface and you will get information about all sources inside, but no information about sources outside. Then our appetite grows. We would like to know not only amount of sources, but how they are distributed. We take small volume, divide by volume, this integral, we get density. How left part is called. It has name divergence. Simple, very simple. DIV, divergence. So, it's not difficult. It's a question, what is difficult? To know new fact or to know what is behind. So I don't think it's difficult to know new fact. It's interesting always. Especially it's universal. Suppose geophysics will be closed, you will go to another area. Again, divergence will have the same meaning, and or vice versa. So, when I write divergence electrical field, I hope from this moment you understand what is it. It's a ratio between flux through closed surface of flux of electrical field through small closed surface divided by volume. And physicists don't care what is the expression. He cares what is the meaning. What this device shows? Density of sources. So, this equation was obtained from Coulomb's law. So using Coulomb's law, we mentally, let us imagine we calculated flux, then divided by volume, and got this expression. That's my goal. Don't worry what is the analytical expression. Don't worry. Think about meaning. So let me check together with you. What is divergence electrical field at this point? Divergence electrical field. What is divergence electrical field? Without thinking what kind of operations you have to do. Simply from the meaning. What does flux through closed surface show? Amount of charges inside of this surface. Correct? Huh? Correct? We make agreement, gentleman agreement. We believe again great masters. It's a question whether you would like to accept new fact or you don't. So you have, it's a simple common sense. So we assume that Gauss was great man, for instance. And let us assume he was great man. So let us assume that flux through closed surface shows amount of charges. Clear? Now I take small volume. What does flux show? Amount of charges inside of this small volume. If I divide by volume, what I get? Density of charge. So simple, you see? Only we have to rotate our gray cells, and that's all. Very simple. So, again, we don't care what is the mathematical expression. One of you know for sure. Take flux, divide by volume, you got it. Now, if I instead of gravitation, electrical field, write gravitational field, the density of masses. If I write velocity of acoustic waves, density of sources acoustic waves. So it's universal tool. Otherwise, I would not bring your attention. Now, again, back to my question. What is the divergence electrical field at this point? Think as physicist, not mathematician. Do you have charge here? Between you and me, do we have charges here? What is your feeling? Huh? Maybe few ions, but positive, negative, we don't. Moisture, it's dry, not very dry. So, no charges. So, brainly we say divergence electrical field is 0. Huh? Ready? Simple. Now, let me look inside of the table. Divergent gravitational field. What would be divergent gravitational field? With accuracy constant. Density of wood. Now, what is the divergence of gravitational field at this point? Without ink. Huh? What is the density of error? Then let us not be picky. What is the density of? Is it possible to compare with density of wood? No, 0. Correct? You see, now you know what does divergence mean. Otherwise, one more step, we will know how to build Maxwell equations today. Now, we have a few minutes more. We started when? So it's time. Very close. Okay, 2 minutes more, that's we will stop at least with this device. Now, so that's how we derive this equation. I will tell you, we will not derive. We only think. Then I will explain why we have to do. So what I'm doing now, maybe I missed point. It's very bad, but I will try to remind. We found out that Coulomb's law is useless. So we are building new tools. How to solve forward problem. That's what we are now. Otherwise we will not understand Maxwell equations. So this is one of the equation. It has name. Second equation of electrical field. Now, in order to stop, to accomplish this part, mathematicians, and let us not discuss this question, found much more convenient expression for divergence instead of ratio. You remember? Divergence by definition, flux, electrical field through closed surface divided by volume. So mathematician knows very well, engineers also must know, integration is very unpleasant procedure over surface. So is it possible to get rid of it? Is it possible to find simply way? Last century it was found way how to get rid of integration. Not to get something new, but make it simpler. Let me write you one example of this expression. Which operation simply? Differentiation or integration? You have function. What is easy? To differentiate function or integrate? Huh? So others also knew, as you know, so they naturally replaced integration by differentiation. And one of the lovely expressions in Cartesian system of coordinates is dx plus dy. Can you guess what will be last step? Yes, that's very simple. dz over z. Meaning is the same. It's a little unpleasant expression. It can create misunderstanding. And unfortunately, most places I found this misunderstanding. Oh, divergent sum of 3 derivatives. Therefore, it characterizes rate of change of the field. No. Not at all. It still has one goal to show, do you have at vicinity of this point source or you don't have. This derivative looks like dangerous, but if at this point, gravitational masses, for sure gravitational field changes, and each derivative is not equal in general 0, but these derivatives are very clever. They have agreement. They cancel each other if no sources. So it's only superficial derivative. In effect, it's only litmus paper which shows do you have source or you don't have source. Let us stop here, and then I will continue. That's the most difficult part.
Okay, so, walk around from morning tea.
The morning tea is up.